Hi, so today is the little answer period for week one. Week one, I'll use a red letter with big boom. That's what we were looking at. We were looking at explosion. That's what that's a picture of, an explosion. What you guys saw was explosion, fire, smoke. Some of the questions were, why did the guy blow up his yard? How did it happen? When it explodes, why does it make the shape it does? How much damage do they cause? And did people intend to make those explosions? So let's look at what we saw. We saw explosion, fire, smoke. These are all different types of explosions. So something exploded, right? That's the word we're all familiar with. And explosions can be extremely powerful. Let's look at the one in Beirut. Here's the before and after. You can see here we have, buildings that are intact. All this stuff right here. And then the one below it, it's completely gone. And so they can be way, way powerful. So where does all this energy come from? So where did the energy come from that blew down this building right here that's now completely gone? Where did that come from? And why did the explosion take place? And so the other explosion that we saw was when that guy blew up his yard. And so the first question is, why did the guy blow up his yard? So there has to be a reason for the explosion. And so that guy, we saw that he used a match and he ignited something. And I saw in the article that he said, I had no idea that this could happen. Luckily, the damage was only contained on the lawn. If I had been standing closer or the table had hit me, it could have been fatal. And so what this guy was trying to do, the intention of this was why did he blow up his yard? He was trying to get rid of cockroaches. Cockroaches nest under layers of decaying material. So if you have the ground down here, and then you have different layers of stuff with leaves and all kinds of other junk, and then you have grass on top of it, there can have little burrows under here, that they can grow in and lay eggs, so on and so forth. So he was trying to get rid of these guys. And so how did it happen? Which was another question. He used gasoline. And what is gasoline? Well, if we look at the chemicals that make up gasoline, it's made up of C's and H's. See these C's and H's right here. CH, 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 CH. There's an OH. There's a CH, CH. And you have these lines in between them. And so what the lines are doing is these lines right here, I'll put green dots on all of the lines. Maybe I can make it a little bit bigger. Green dots on the lines. There's two lines, single line, double, single. All these lines are holding these things together. They're holding the C's and the H's together. And what happens when an explosion happens is the energy that's tied up inside of these bonds holding the things together, it explodes, and those bonds are where that energy comes from. So there were lots of C's and lots of H's. So let's look at that. On the periodic table, here are our H's, and here are the C's. And if we look at these guys, we can see the H has a 1 above it, and the H has a 1 below it. And here we have the C has a 6 above it, and the C has a 12 below it. And so these two numbers are kind of important. And so what this is right here, this periodic table of elements, everything that we know, bricks, you, me, urine, trees, everything is made up of these building materials. These are like bricks. Every one of these things are bricks. Diamonds are made out of certain things, and they're all held together by those little bonds, those little lines. And so in terms of gasoline, we have C's and H's. We had a lot of those together, and that's what holds those together. So if we look at an H, what that H means is, why don't we use this color? So you have an H and you have a C. What that little 1 means up here, and what was the number above the C? It was a 6. It was a 6 above that. So what that means is we can, maybe I can, how can I erase this guy? Here's my eraser. So we can erase this guy. And so the H, because it has a 1 around it, what that means is that there is 1 electron that orbits around this thing. And so it just cruises around this. And this is called an electron. And I put a minus up there because it has a minus charge. Because it's just like a magnet. And then the H portion, that consists of, because there's 1 there also, it has 1 proton and 1 neutron in there. And so what happens is this guy just cruises around at a high rate of speed, cruises, but you have to remember it's not necessarily just going in one plane, it's going all over the place. So it ends up looking like a tennis ball where this thing's spinning around, but it's also spinning, and so if you were to imagine that looks like a tennis ball, the protons and the neutrons are on the inside, and then you have an electron going around it, and then you have a bond that's holding that together. Well, the C had 6, so that means that there are 6 electrons. 2, 4, 6. You have 6 electrons cruising around there. And so these are all minuses. And you also have a whole lot more protons and neutrons. So if we do this, the protons and the neutrons, and you also would have 6 protons and 6 neutrons. So now we have something that's a lot more complex. So maybe if we had 6 protons, and then let's make the neutrons green, and then our electrons, we had 6 of these guys that were that were revolving around it. 2, 4, 6. So it kind of looks like that. And remember, all these electrons are spinning wildly all around it. Well, this is spinning all the way around it like this. All 6 of these guys are, right? And imagine that looks like a ball. But now you can have a bond that holds these guys together. You can have a bond that holds those together, and that's one of those lines that was right here. And sometimes you can have a double bond, which is really hard to hold, which is holding it together even more so. And because you have these bonds here holding the C and the H together, now sometimes I need another color, but we'll use green. But sometimes the electrons can go like this. And so what happens when you have an explosion is you break this bond right here. We break this bond, and the energy that was tied up in holding this together goes poof, and it goes out in terms of an explosion. But something has to set it off. And so if you look at wood, you need to have a lighter that sets it off. And then the stuff that comes off is the energy, but then the energy can come off as smoke too, which is what carbon is. And so when you have the individual particles that come off, you can have carbon that comes off all by itself. And then you can rearrange some of this other stuff, and we know there's oxygen out here, so you can end up with water also. And now just a little bit that you guys have learned about atoms, you can probably see that H2O would be 2 H's and an O. And they're probably bound together with these little bond things. And then you can make these things. But when you start breaking these bonds, boom, you start blowing stuff up. And so a question was, when it explodes, why does it make the shape that it does? Well, if you have a bomb that's like this, and it's perfectly round, and then you ignite it or detonate it. When I say that, that means breaking those bonds. When that happens, the explosion will go out like a hand grenade, will go out in all directions. If you were to make a shape like this, and then you put the bomb in here, the explosion, and you detonated it, would be directional. So you can make it what's called a shape charge. And a bullet is kind of like this. We're directing the explosion to happen in one particular area. And so it goes in one particular direction. And so when it explodes, why does it make the shape that it does? And the answer would be, it depends on the environment that it's in. If it's a round ball floating in the air, it will go unidirectional. If it's made in a shape, it will go in a specific direction. And so the next question is, how much damage do they cause? Well, they can cause enormous damage. Enormous damage. And how about, to answer this, how much damage do they cause? A lot. But it depends on what is being exploded. And so if we remember that carbon and oxygen, they had 1 up here and then they had 6 right here. If we look at something like uranium, uranium has 92 up here. 92. So you can imagine having 92 protons, 92 neutrons, and then you'd have 92 electrons that are all orbiting around this thing, 92 of them. And then you would have to then break those bonds apart, and then you would release a lot of energy. And just to combine the shape charge with a nuclear bomb, the way those work is you would have a bomb like this, and then let's say you have an inside core. And then you would have right here, you have something like TNT or gasoline or something. And when it explodes, there's a space in this inside, so the explosive charge goes inward where the uranium is. The explosive charge goes in because it's a really strong casing. So the explosion all goes inward, and then it breaks all the bonds of that uranium, and then, let's see if I can do a big one, and then this is huge when it comes out. So you're using a shape charge to make an explosion with gasoline or TNT, which then goes inward, which then breaks the bonds of the uranium, which then blows that out and then has a humongous explosion like this one. This is an underwater nuclear test. That thing was like a mile underwater when it blew up. And so the last question was, did people intend to make these explosions happen? Yes. And no. And so in the ones that we saw, yes, they did. But what happens a lot of time is, let's say you might have a boat. We'll put a cabin on that boat with some windows. And then you might have a propane tank on top. And then you have lines going into the boat. And then you get a break in your propane line. The propane fills up the bottom of the boat. Let's make propane in red. It fills up the bottom of the boat because it's a gas and it's heavier than air. And then the bilge pump goes off, but you have a short in the wire. And so when the short in the wire sparks it and is enough to break apart those C's and H's, which then releases the energy from these bonds and then blows your boat up. And you know what's really funny is these are all combustion explosions. And these exact mechanisms happen in your body billions of times an hour. And this is where we get our energy. We get our energy from breaking these bonds. That is where our energy comes from. It's a combustion reaction. You have some carbons, and then you have some air. Look, I'm breathing in. We have air that comes in. What comes out? Carbon dioxide, which looks like this, plus water. That's a combustion reaction. We're breaking the bonds between these carbons, which might look like this. You know, you might have all these C's strung together, but remember, we're breaking these bonds to make an explosion, and we don't want it to be too big of an explosion. It's a little explosion, teeny tiny. But we're still breaking those bonds, and then we're using this energy to work our muscles or make our stomachs digest food. That's why we have to breathe oxygen right here. And then what do we breathe out? We breathe out carbon dioxide, and we have to pee. That's where the water comes from. If you look at a car, you'll impress your friends with this. A car does the same thing. It breaks the bonds of carbon. It adds oxygen through the carburetor. You have a spark which ignites it, and it blows out CO2 and O2. This is why exhaust pipes drip water. That is where the water is coming from. It's coming from a combustion reaction. So kind of cool, huh? So, did people intend to make these explosions happen? Yes, they certainly did. He lit a match and he did it, but sometimes there's unintentional ones. But we need these explosions to happen in our body so we can get energy from them. That is all.